Hello, welcome to this new video. In this video we are going to see the concept of closed set and open set and closed set defined in a metric space. A subset of a metric space X together with the metric D is an open set with respect to the metric D if O is the union of open balls. See, if we can express a subset of the metric space as the union of open balls, if you can write it completely as the union of open balls, then such a set can be called an open set. The family of open sets defined in this way is that can define. See, you can imagine the collection of the family of open sets which are defined in this way for a given metric space, and that can be called the topology. That can be defined as the topology for the given metric space. So given the metric space X, you can together with the metric D, then we can define open sets. We can consider open sets, and then you can consider the set of all open sets, so the family of all open sets, and that family of open sets can define a topology for the given metric space. We can now related to this concept, we can define the closed set of a metric space. A subset C of the metric space X is said to be closed with respect to the given metric D, provided that its complement in X, the complement of what? It's the complement of the given set C. That is a C complement. If the complement of the set C, if that complement is an open set with respect to the given metric D, then we can say that the subset C is a closed set. So the closed set, the concept of closed set is defined related to the open set. So after defining the open set, after understanding the meaning of an open set, we can understand the concept of a closed set. Okay, now we have a theorem to discuss. Let's go through the statement of the theorem. So let O be a subset of the metric space X, D, XD. Then the following statements are equivalent. We have three statements. We have to prove the equivalence of three statements. Here what is given? Here O is the subset. A subset of the metric space XD is given, and so is the subset. O is that subset. Then given that subset O of the metric space XD, then we can define. We can prove the equivalence of the statements. So statement 1 is O is an open set, and statement 2 is for each X in X. X is a point. For each point X, for each point X in the given set O, for each point X in O, there is an open ball. There exists an open ball, or you can give an open ball. You can find an open ball B X comma epsilon X. See, this is the radius of that open ball. Epsilon X is the radius of the open ball, and the center of the open ball is the point X. So you can find, or you can give an open ball B X epsilon X for some positive value, positive number, positive real number epsilon X, which is contained in O. So this open ball, what has its property? It's the importance of this open ball is that it is completely contained in the given set O. So actually, when does it happen? Actually it happens when the taken set O is an open set. So if the taken set O is an open set, then you can find an open ball centered at every point belonging to that open set. You can find an open ball which is completely contained in O. Also, if if O is not equal to X, so this is the situation that the taken subset is not the entire metric space. So assuming that O is not equal to X, the entire metric space, then the first two statements are equivalent to the next statement. See, the statement 1 and statement 2 that we have here given. These statements are equivalent to the next statement, means the third statement, which that third statement is for each X in O. See, the distance from the point X to X, distance from X, the distance of X comma X here, it is not x minus O actually, and this is there's a correction here. This correction must be noted, that is the distance here, it is distance between X and X minus O. So that will be greater than 0. The distance between X and X minus O is X minus O is greater than 0. Okay, to prove the equivalence of these three given statements, see, we have some specific way to proceed. See that first of all we prove that 1 is equivalent to 2. First, what we want to do, we are going to prove that 1 is equivalent to 2, and then we will prove the equivalence of the statements 2 and 3. After that, after proving the equivalence of the statement 1 and 2, we will prove the equivalence of the statement 2 and 3. But for proving that equivalence of the statements 2 and 3, we additionally assume that O is not equal to the set O, the subset O is not equal to X, that we additionally assume. It's because because the distance from from a point to the empty set is not actually defined. It's because in the third statement, actually this must be corrected. The distance from the point X to X minus O, actually that is the term here, X minus O. So when O is equal to X, assume that the situation in a situation we have O is equal to X, then when we take X minus O, then you will get the empty set. X minus O will be empty set. That means here you are going empty set here, and in such situation the distance, when we measure the distance from X to an empty set, actually that is not defined. So in order to avoid this situation, this strange situation, you will get a strange situation there. That means you are measuring, when you have an empty set here, you are measuring the distance from an empty set to an element of capital X. That is the point X, small x. That is the point X. Okay, from that situation should be avoided, because that distance is not actually defined. So in order to avoid that situation, we consider this this additional condition. Okay. So avoiding that situation, you can prove that the statement 2 is equivalent to statement 3. So let's start the proof of the statement 1 implies 2. So first we can show that the statement 1 implies statement 2. So for that we can assume that O is we can assume that we are given an open set, and that is we are given an open set which is named O. let O be an open set. So we begin with that that statement. We take an open set O. Okay. Then we want to show that. Then what we want to show? We want to show that there are for each x in O. We begin with the open set O, and the next we want to show that for each point x in O, there exists an open ball. There exists an open ball b x comma epsilon x. What does it mean? There exists this is an open ball. This is an open ball with a center at center which has center at x and radius epsilon x. So then you can find an open ball bx epsilon where epsilon x is a positive real number having the positive radius epsilon x and centered at x, and b and that open ball bx epsilon x is contained in O. It is then contained. You can show that it is completely contained in O. So for that, for proving that, we follow these steps. Since O is an open set, it is the union. We know that by the definition, by using the definition of open set, you know that if there is an open set, if O is an open set, then it can be written as the union of open balls, right? Yeah, we have used that definition. We have that definition for open set. So using that definition, you can say that it is the union of open balls. So if you are picking one point, say x, belonging to the set belonging to O. Suppose you are taking a point that is x. X is an element of O. X is an element of O. Yeah. Then due to this definition, due to the statement, this statement part of the definition, then you can find an open ball BAR which contains that element x. See, you can find an open ball BAR, and this open ball has a center at A and radius R. For some, this R is some positive real number. Okay. Such that x is then x belongs to that open ball. Then you can find. Yeah, it's because you can write the open set as the union of open balls. So, and then you can see that the distance from x to A is then less than R. Why? Because the point x is in that open ball. Because of the reason, since the point x belongs to this open ball. So due to that reason, you can write that the distance from x to A is less than R. See, for getting the idea very for understanding this idea easily, then you can we have a figure is given here. You can refer this figure. Now you can see that in this figure the open set is the open set O is given, and this is the open set O. Okay, therefore this is the metric space, and this red rectangle. The rectangle which is given in red color, it represents the metric space capital X, and here, even though here you can note that O is not that it is not named here. Actually, this is the open set. The boundary is it is marked by using this the movement of the cursor. So you can see that this is the open set, given open set. So you can give here the name of the open set O, and then what we do, you have to consider the element that an arbitrary point of that open set is then taken. So see, after considering that open set, you can see that this is the set x minus O. This outer portion is x minus O. Okay, then we then arbitrarily we take a point of that open set, and that point is given is represented here in red color. We take we take a point, it is named x. We take an arbitrary point x of that open set. Then since this open set is made up of open balls, or since we can write this open set as the union of open balls, you can suggest, or you can find an open ball which contains that point x. See, that open ball is BAR. Here you have that it is given here BAR. This is that open ball, and this circle, this bigger circle, is that open ball, which that open ball contains given that taken arbitrary point x, and that open ball has A as the center and R is the radius of that open ball. See, here you can see that this is the radius and A is the center. But an important thing is that by since the radius of that open ball is R, you can now find another. You can find, or you can take another open ball which is completely contained inside that bigger open ball. So that is the important point you should remember at this moment, because the distance, that by referring the distance between the point x and the center of that first open ball, the bigger open ball, that is A. So you can see, you can take that distance between x and A, that is d x comma A, and you can see that distance is less than what? Of course, that distance will be, because this point x is inside that inside the bigger open ball. You can clearly understand that the distance between x and that center of the open ball will be less than the radius of that bigger open ball. That is, it is less than R. So that is stated here, and that thing is stated here. Then clearly distance between x and A is less than R. Yeah. So from this figure it is clear. That means if you choose a quantity which is less than we are now going to take a quantity which is less than R minus that is less than R minus the distance between, okay, and it's because we know that we have that relation, the distance between x and A is less than R. Okay, now we can consider the quantity R minus distance between x and A. Then what will be that quantity? Because subtracting, if we transfer this quantity to the right side, then we get that R minus d distance between x and A. That quantity is a positive quantity. That 0 is less than R minus d of x comma A. So okay, this quantity, this is an important quantity. It's a positive quantity. R minus the distance. R minus the distance between x and A, and that quantity, since it is positive, you can define epsilon x. Epsilon x is another quantity which is the maximum, it is equal to this quantity. Okay. So by choosing that quantity, R minus the distance between this is the distance from this point x to the boundary of the bigger circle. Okay, the bigger ball. The distance between R minus distance between x and A is equal to the distance from the point x to the boundary of the the outer circle or the bigger circle. So by taking the quantity epsilon x, see, by taking the quantity epsilon, some quantity suitably you can choose the quantity epsilon x, which is a quantity which is suitably taken such that it is less than, if you take epsilon x, a quantity less than r minus, less than this distance from x to the boundary of that that outer circle or the bigger circle, and that is epsilon x is less than r minus the distance between x and a. Okay, if you choose that epsilon x in that way, and after that if we define a ball, another ball with the center at x, here you can see that inner, the smaller circle or smaller ball, if we define that ball in this way, that is which is centered at x and having that the radius epsilon x, that is that quantity, using that quantity that we have defined now, using that epsilon x, then that ball will be then clearly inside. If we define that ball in this way, you can see that ball will be completely inside the outer ball, or inside the bigger ball. It will be inside, it will be contained well inside the outer circle. Okay, and due to that reason we get by proceeding this way, we get that we get a new ball. So first we choose a bigger ball, and after that, using some relationship using the relationship between or considering the relationship between the distance of x and distance of x from a and the quantity r, the value of the quantity, value of the radius of the bigger ball, we define this epsilon x, the quantity epsilon x, and using that we define an inner ball. And so it is clear that this inner ball is well inside that outer ball. So and therefore what we can now say, and we therefore yeah, in this way we get that using that geometry, we, since this geometrical arrangement itself says that b x epsilon x is well inside that outer ball. Okay, and thus we have now completed the proof of the first part, that is 1 implies 2. It's because that states that the existence, it says about the existence. Actually we are trying to find an open ball b x epsilon x that is well inside the given open set. See, this is that open set, and since this open b x epsilon, the open ball b x epsilon is well inside the outer open ball bar, and but bar is actually is present inside the open set. So it is clear that b x epsilon x is well inside the open set. Okay, thus we have completed that. We have now arrived at the fact that we have derived the fact that, or we have showed the fact that there exists an open ball bx epsilon which is centered at x and having a radius epsilon x, and that epsilon x is a quantity which can be related to x, that can be attributed to this x, such that this bx epsilon is contained in the open set. Okay, thus we get that 1 implies 2. We have completed the proof of 1 implies 2, and okay, this is the figure which illustrates 1 implies 2. That is the caption for this figure. Okay, and then and therefore see, and that part is also explained here, since epsilon. Okay, all those things we have completed actually, and this is the then we make the claim that the open ball bx epsilon is completely contained in. Okay, and then that was actually the explanation. I have completed that explanation using this figure, but in using fully mathematical way, using using some algebraic operations or algebraic steps, actually we can establish the fact that the smaller ball is well inside the outer ball, and as a result of that it is contained in the open set. So for that we are going using some suitable steps, we are going to show that fact, and so that means we are going to make the claim that Bx epsilon x is a subset of BAR, and we can now prove that this claim is true. So for that, how can we show that? For that we take a point y in y belonging to the open set B x epsilon x. See, this bracket is missing here. Here we take first, what we are going to do is, this is that point, a third point, a new point y is taken, and this point y, and this is that point, this point in brown color, and that point is a point arbitrarily taken inside which belong to the inner ball, and that's why we are writing that y, that point y is an element of Bx epsilon x. See, we take an arbitrary point y belonging to the set Bx epsilon x. Okay, after that we will show that this y is an element of BAR. Okay, by taking an element of Bx epsilon x, we shall show that y belongs to BAR, and this is the statement we want to show. Y is an element of BAR. How can we prove that? Okay, and for that we are going to find the distance of y from the point. The distance of y to the point A, we are going to find the distance of this point y to A. We shall show that this distance is less than r. If we can show that the distance of the point y to the point A, this A is the center of the outer ball. If we can show that this distance from y to the point A is less than r, that implies that the point y is inside that outer circle, outer ball, the bigger ball. Okay, for that we can use that that non-fact. So for that, that can be written. We can begin the step for doing that. We can begin the step D, distance between y and A, d of dy comma A. It is then less than or equal to, using the third point. You have a third point here. If we have y here and A here, the point A, and we have third point x, the third point x. When we have three points, you can apply that axiom of the metric. We can apply the axiom, the third axiom of the metric can be applied here, and that is the triangle inequality. And using that axiom, we can say that, considering x as the third point, d of y comma A is less than or equal to d yx plus dxa. But dyx, the distance between y and x, what is that? This distance between y and x. Okay, that distance will be less than. Then considering that, here we consider the inner ball. Considering that inner ball, since y is inside that inner ball and x is the center, then it is clear that distance between y and x is less than epsilon x. So you can replace that dyx by epsilon x. That is done here. When we replace that that quantity by epsilon x, we get that here epsilon x plus dxa. Okay, and then you can replace this less than or equal to by less than, clear less than symbol. Then this quantity, dx, then epsilon x can be this epsilon x can be replaced by r minus d of x minus x comma a. It's because we have chosen that epsilon x equal to r minus d of x minus a. Since we have chosen that in the previous step, in the previous step you have chosen that epsilon x equal to r minus d of x minus a, so you can substitute that quantity there, r minus dx minus a, then we have this plus dx minus a, this cancels and we get that it is equal to r. Okay, and so we get that since the distance, that is what does it mean? It means that distance from y to a is equal to r. It is there less than r. Okay, this distance from y to a, distance between y and a is less than r. That means y then belongs to this element, y belongs to bar. Okay, therefore clearly we get that bx, the ball bx epsilon x is a subset of bar. It's because this is true, this inclusion, that means y is an element of this statement, y an element of bar is true for all arbitrarily for all point that are taken arbitrarily from the open ball b x epsilon x. Okay, and therefore you get that 1 implies 2. Next we are going to show that 2 implies 1. Actually this part, the proof of this part is very simple, because it that means it follows easily, because if 2 is true, then we can, it can be, if true is true, then we can find an open ball. We can find an open ball, at least one open ball. See, we can find at least one open ball which is centered at the point x in O, and which is contained and is completely contained in O. See, if 2 is true, what does the statement 2 states? It states that for each x an element of O, x in O, there exists an open ball bx epsilon x. Okay, using this fact, since there exists an open ball bx epsilon x which is centered at x, okay, when we consider by varying the points inside O, we get that for each and every element of O there exists an open ball that is bx epsilon x. And therefore we can say that we can then conclude that the subset O, see, the subset O can be written as the union of open balls, a collection of open balls, and that means O is an open set. So we can say that that is the end of the the converse statement. Okay. And okay, this is that's the end of that. After completing that part of the proof, and we can now think about proving 2 implies 3. How can we prove that 2 implies 3? But for in this statement we have to exclude the possibility that as we have previously explained, that we will avoid the possibility that x is equal to O. So in our consideration, foregoing discussion, in the discussion, foregoing discussion, we will assume that the set, the open that subset taken, and the subset is not equal to the entire metric space. Okay, and then See, we consider an open ball. Since there exists, since the statement 2 is true, then we can give an open ball bx epsilon x for then there is an open ball bx epsilon x which is centered at x and x where x belongs to the given subset O, and then any point within a distance of epsilon x. What does it mean? That it means that any point within a distance of epsilon x is in O. See, since bx epsilon x is completely contained in O, and therefore any point which is within the distance, any point within the distance of epsilon x from x is in O. So the distance from x to distance from x to x minus O, actually this is not x minus x minus O, from the distance from x to x minus O must be at least, and this is a statement that must be corrected. Actually it is x minus O, that is from x we are removing O. X minus O must be at least epsilon x, and thus the distance from x to distance from the point x to x minus O must be greater than 0. Actually it must be greater than 0 for each x in O, and thus this proves the statement 3. Next we shall prove that the statement 3 can imply statement 2. For that we assume that 3 holds. The statement 3 is true, and that is the distance from x to x minus O is a positive number alpha x. Let's take that positive number equal to alpha x. Then depending on, but this quantity varies depending on x, and this means that the distance from x to any point which is outside O must be at least must be at a distance of at least alpha x, or the distance from x to any point outside O must be greater than or equal to alpha x. So any point within a distance of alpha x of x must be in O, and that means bx alpha x is a subset of O. Okay, and therefore we get the statement true, and we get that there exists an open ball with the center at x, and that is contained in O. So we get the statement the 2, the second statement. Okay, that's the end of the equivalence of the 3 given statements. These statements actually explains the properties of the open subset of a given metric space. Okay, thank you for listening.